All right. Okay, thank you for a nice introduction. And well, the topic of my talk is, well, it's about bicontinuous semigroups. You heard the talk before by Christian about it. And well, here the topic is equicontinuity and tightness of bicontinuous semigroups. And this talk is based on a joint work with Felix Schwenninger from the University of Twente. So let's have a quick look at the outline. So probably if you attended the first talk, you already know what a bicontinuous semigroup is. And well, I can maybe go quickly through the motivational part and some of the definitions because you saw them already. We will start with the Gauss-Weierstrass semigroup. See again that this is a bicontinuous semigroup. Then we will talk a bit about the mixed topology. You already saw a special case of the mixed topology in the first talk. And then we will talk about equicontinuity and equitightness of bicontinuous semigroups, because you have several topologies here. You have to choose, okay, or you have to find the right topology for which the semigroup is equicontinuous. So let's start with the example. Well, this is the example which comes from the heat equation now, where your initial values are from the space of bounded continuous functions here on Rd. And well, you saw the domain in the first talk as well. If you have that the dimension is 0, then the domain of the Laplacian here is the space of bounded continuous functions, such that for every p, the function belongs to this local Sobolev space, and such that the Laplacian or the weak Laplacian applied to f is again a bounded continuous function. And if the dimension is 1, then the domain is just the space of twice continuously differentiable functions on R, such that all derivatives up to order 2 are bounded. And you can, for example, find in a book by Lorenzi and Bertoldi that the Laplacian with this domain is the generator of the diffusion semigroup on CB. And this is just given by, well, at 0, this is just the identity. And if t is bigger than 0, then it is the convolution of your function f with the Gauss-Weierstrass kernel. And then you get, well, that you can have a solution of your Cauchy problem here by applying your semigroup to the initial value. And what Christian already mentioned in the first talk, this semigroup is not strongly continuous with respect to the supremum norm on CB, but it is strongly continuous with respect to weaker locally convex topology, namely the compact open topology. So this is a special case of a bicontinuous semigroup. And here are again the assumptions, which, so you have always such a triple X, the norm and the weaker Hausdorff locally convex topology. And you assume that your space with the norm is a Banach space, and that if you have equipped it with a tau topology, that it is sequentially complete on norm-bounded sets, which means every norm-bounded tau Cauchy sequence is convergent, and you have that the tau topology or the tau dual is norming for the space. So this means that you can replace in the usual norm formula the norm Banach space with the tau Banach space. So in the usual norm formula, you have at this position the norm dual, and you can replace it by the tau dual, which is in general a smaller subspace, or just a subspace of the norm dual. And you can rephrase this norming topology as well. Namely, this is a condition you saw as well, that there is a system of seminorms that generates the tau topology such that you take the supremum over all of these seminorms, you get the normal. And in the first talk, these three assumptions were then, if you combine them, called that the space is biadmissible, or the triple is biadmissible. Okay. And well, now the definition of a bicontinuous semigroup, which was introduced by Franziska Kühnemund in her PhD thesis in 2001, is that this is a semigroup of continuous linear operators here from x to x with respect to the norm on this space, such that it is strongly continuous, but only with respect to your weaker topology, the tau topology. It is exponentially bounded. And whenever you have a sequence in X, which is norm bounded and tau convergent to some limit X, then the tau limit of your semigroup applied to the difference is 0, and that locally uniformly for all t in the non-negative real line. Okay, and then we already saw this in the first talk, this Gauss-Weierstrass or diffusion semigroup is an example of a bicontinuous semigroup, namely if you take as X the space of bounded continuous function with the supremum norm, and as the tau topology, the compact open topology, so you take suprema on compact subsets of RD. And then you get that this is a bicontinuous semigroup with respect to the compact open topology. Okay. Now we can look at the more general setting here. Here's our Laplacian here by generator of a continuous semigroup. This is something which was introduced in the first talk as well. Namely, what is a generator? Well, it's defined like in the setting on Banach spaces, but you take here the limit not with respect to the norm, but with respect to the weaker tau topology, and you define your domain not only as the space of all x where this limit exists, but your, well, let's say your different quotient should be bounded in the norm near 0. This is an additional assumption here. And then the question, for example, is if I perturb my operator A here by some operator B, let's say a linear operator B, I know if I only have A here, I know a solution, and of course I know a solution of the perturb, that there is a solution of this abstract Cauchy problem if A plus B is again the generator of a bicontinuous semigroup. Now then the question is, okay, which perturbations are, for example, allowed? And there are quite much results on that for bicontinuous semigroups and for locally, for C0 semigroups on locally convex spaces. And usually they need something like equicontinuity with respect to some topology. And so the question is, when is a bicontinuous semigroup locally equicontinuous, and with respect to which topology? And there is a related notion to equicontinuity, which is called, or sometimes called tightness or equitightness. And this is something which, well, plays a related role in the continuous thing as in the setting of equicontinuity and the setting of on locally convex spaces. And so you can see, well, here are some papers with affirmative results which answer this question. And well, the first one here from 2015 from Jakob Wegner Wintermeyer, and the paper you already saw in the first talk by Albanese and Tornay, they need some equicontinuity conditions in their theorems or in their perturbation results. And the equitightness condition appears in perturbation results for bicontinuous semigroups, for example, in papers by Balem Farkas from 2003 and 2004, and with his co-author Esther here in 2006, and in papers from Christian Budde, who gave the first talk in this session here from 2019 and 2021. So the question here is, which is the right topology for which the bicontinuous semigroup is actually locally equicontinuous or equitight, which I will explain in some moments. Well, the right topology to choose is a mixed topology. Because if you think again of the Gauss-Weierstrass semigroup, this one is not locally equicontinuous with respect to the compact open topology. So you need a different topology if you want to have equicontinuity. And that one is a mixed topology. So let's go back to the definition of bicontinuity, namely of the part here, which is colored blue. So we have that for any sequence xn, which is non-bounded and tau convergent, that this here holds. Well, then one may ask, is there maybe a Hausdorff locally convex topology where what is written here in blue is actually convergence of sequences in this topology? And there's at least one, you saw it in the first talk, namely the mixed topology. This was introduced by Vivega in this paper from 1961. And there is a Hausdorff locally convex topology, which is usually denoted by gamma, such that convergence of a sequence with respect to this topology is equivalent to norm-boundedness and tau convergence. It's the finest linear, so it's even the finest linear topology which coincides on norm-bounded sets with the tau topology. And as I said, it is called the mixed topology. So sometimes it's hard to describe, so using seminorms, this topology, but you saw an example in the first talk, namely on CB. And this example goes back, I think, to Book in a paper from 1958. Namely, when you have CB with the norm, with the supremo norm as a norm and the tau topology as a compact open topology, then this mixed topology is generated as a weighted topology. So you take the suprema of the absolute value of a function multiplied with C0 functions. And then you get a whole system of seminorms, and this system actually generates the gamma topology. This wasn't introduced by Book as a mixed topology. He called it, I think, the strict topology. And it wasn't interested in bicontinuous semigroups. He was interested in the question, if I take CB, and usually if I take the dual space of CB, this is an ugly space. In contrast to if I take, for example, the dual space of C0. So then he asked, or he wondered whether there is a locally convex topology on CB such that CB with this topology has a nice dual space, namely a space of measures. And then that was the way he introduced this topology. If you take the dual of CB with respect to this topology, you get the space of bounded radon measures on RD. And this is why Book was interested in this topology. And later Cooper showed, I think, at least in a paper from 1971, that this topology is the mixed topology on CB. If you want equicontinuity results for locally convex spaces, you can have them sometimes for free if you have nice spaces, namely if you have, for example, a Fréchet space, which is a complete metrizable space. The troublesome part here is that this space with a mixed topology is not metrizable, so you can't use some kind of uniform boundedness principle or Banach-Steinhaus theorem to get equicontinuity with respect to the mixed topology. And well, then you can say, well, there is such a theorem for Barrett spaces, which are more general than Fréchet spaces, but this is based, at least if it's not a trivial space, which means that the mixed topology coincides with the norm topology. So one has to do this a bit different. So what does equicontinuity with respect to the mixed topology mean? Well, the same, roughly the same as for a norm or some other locally convex topology. You have here, okay, it's locally gamma equicontinuous. Locally means on every such interval. If for every semi-norm in a system which generates this gamma topologies, there is another semi-norm and some constant such that you can estimate your semi-norm applied to TT, applied to X by constant times this other semi-norm. And that for all T and all X. So this constant does not, or this constant and this semi-norm do not depend on X or T. And well, what I mentioned equitightness. What does equitightness mean? Well, if we forget about this part here, this part, then this would just be, well, local equicontinuity with respect to the tau topology. But as I already mentioned from in the example of the Gauss-Weierstrass semigroup on CB, this one is not equicontinuous with respect to the compact open topology. Well, but if you add on the right-hand side here some epsilon times the norm, then you get the notion of equitightness. And one then will see, so what one always has is that equitightness implies local equitightness implies local gamma equicontinuity. And then the question is, when does the converse hold as well? And do my bicontinuous semigroup fulfill or have these properties? And there's a result by Felix Spenninger and me from 2000. I think that it's in the preprint from 2021, and it appeared this year in the Journal of Mathematical Analysis and Applications. For example, if your topology tau is metrizable on the closed norm unit ball, and your closed norm unit ball with respect to your tau topology, then any bicontinuous or any tau bicontinuous semigroup is A, locally gamma equicontinuous, and B, locally equitight, and both properties are equivalent. So the nice part here is this holds for any tau bicontinuous semigroup as long as these two conditions here are fulfilled. If you only have, let's say, let's have a look at it. If you only have the first part here, then you still get this local gamma equicontinuity, but you might not have that this equicontinuous semigroup is equitight as well. And you can generalize these two assumptions as well. Namely, if you replace the first one here by, you can replace this one, for example, by that your space with the mixed topology is C sequential, which means that every convex sequentially open set is already open, then this holds as well. This is a more general assumption than that one. And you can replace the second condition here by having that the mixed topology coincides with something which I call the submixed topology. And the submixed topology is actually what was called the mixed topology in the first talk by Christian Budde. So if your mixed topology coincides with the one that was introduced in the first talk, then you have this theorem as well. So this is a more general assumption then. So what are settings where this holds? You saw some of them in the first talk, namely if any tau bicontinuous semigroup on X is locally equicontinuous with respect to the mixed topology and locally equitight. If you're in the setting where X is your space of bounded continuous function on some set, on some space omega, for example, omega equal to RD, that was our example, or more general, if this is a Polish space, or something which is called the hemicompact Hausdorff-Kr space, for example. Every locally compact, sigma compact Hausdorff space is such a space. But there are other ones. For example, if you take the dual space of an infinite dimensional Fréchet space, equip this with the topology of compact convergence, then this is a hemicompact Hausdorff-Kr space. So in this setting, it holds if you take as a norm the supremum norm and as a topology, the compact topology. And examples are the Gauss-Weierstrass semigroup or the Ornstein-Uhlenbeck semigroup or Koopman semigroups, so semigroups which are induced by flows, jointly continuous flows, or the translation semigroup, which is a special case. Then another setting where this is applicable is where your X is the space of bounded radon measures. So the T here stands for tight. That is where the name equitightness actually comes from. So bounded radon measures are tight measures. And if your omega is a Polish space and you take the norm, the total variation norm, and as a tau topology, the sigma topology of the dual pair, the radon measures in the CB space. As I said, if you take the dual of CB with respect to the mixed topology here, you get the space of bounded radon measures. So, and what are examples? Well, of such semigroups, take a semigroup here, take its dual semigroup and restrict it to the space of measures here. Then you have a bicontinuous semigroup in this setting. Another setting which was mentioned in the first talk is if you take X to be a dual space of a Banach space, here a separate Banach space, the norm as the dual norm and the tau topology is the weak star topology. There you can apply this as well. So take an example of such a semigroup in this setting here, take the dual semigroup of a non-strongly continuous semigroup. And what is the mixed topology here? The mixed topology in this setting here is the topology of compact convergence on subsets or on subsets of Y. And a fourth setting here is if you take, again, X to be the dual of a Banach space, here a separable Schur space, and you take for tau not the weak star topology, but the Mackey topology, you can apply the theorem as well. And what is the mixed topology here? It's the Mackey topology again. So the Mackey topology here in this setting is a mixed topology. And maybe I should explain what a Schur space is. This is a Banach space where weakly convergent sequences are already norm convergent. So the most prominent example is if you take Y to be little L1, so the space of absolutely summable sequences. So how much time is left? I think it's not.
I think, let me see. I think we should start with the questions now.
Okay.